Picture the vast cosmic stage where celestial actors engage in a breathtaking dance of destruction and creation. This mesmerizing world of kilonovas, where cosmic collisions between neutron stars or neutron stars and black holes unfold like dramatic performances, casting a radiant spotlight on the universe's most captivating secrets. Kilonovas are no ordinary fireworks. They outshine even the most dazzling novas by a factor of 1,000. Born from the gravitational embrace of compact cosmic partners, these explosions release an astonishing surge of energy that lights up the cosmos across a spectrum of wavelengths, from vibrant gamma rays to soothing radio waves. Delving into the study of kilonovas is like embarking on a cosmic scavenger hunt. These cosmic clashes provide not only a front-row seat to one of the universe's grandest spectacles, but also offers astronomers a golden ticket to unlocking the universe's deepest mysteries. These explosive events yield insights into the creation of precious heavy metals like gold and platinum, and they hold tantalizing clues about the elusive nature of dark matter. With kilonovas, we are on the brink of unraveling cosmic puzzles that have perplexed humankind for ages. So, let's set forth on this celestial adventure as we uncover the immense significance of these astral phenomena in our unending pursuit to grasp the marvels of the cosmos. Now, how do we find these kilonovas? Think of gravitational wave detectors as cosmic ears, finely tuned to the universe's whispers. These detectors, like the impressive LIGO and Virgo, are the microphones for space-time, listening for the ripples created when neutron stars merge. When these neutron stars perform their gravitational collision, they send out ripples in space-time known as gravitational waves. These waves travel across the cosmos, carrying precious details about the merger. Gravitational wave detectors catch these whispers, and when a neutron star merger happens, they not only detect the event but also locate it in the sky. This is groundbreaking because it adds a whole new layer to our observations. Before, we relied on light and other types of waves, but gravitational waves give us a direct line to these cosmic events, without anything getting in the way. Combining the information from gravitational wave detectors with traditional observations gives us a complete understanding of the neutron star mergers. It is like getting a backstage pass to the universe's most dramatic performances, and through this we uncover the universe's deepest mysteries. Gamma ray bursts and electromagnetic radiation observations are like the dynamic duo in the world of kilonovas, illuminating the intricate details of these cosmic collisions in ways that are nothing short of revelatory. When neutron stars merge and give birth to kilonovas, they set off a cosmic fireworks show that spans the electromagnetic spectrum. Among the most eye-catching displays are gamma ray bursts, intense bursts of gamma ray radiation that shoot out in opposite directions from the merger site. These bursts are like celestial beacons, guiding astronomers to the exact location of the kilonova. But the story doesn't stop there. The electromagnetic radiation emitted during a kilonova journey across the spectrum, from X-rays to visible light, and even radio waves. Each wavelength contains a unique piece of the puzzle, providing insights into the kilonova's composition, temperature, and overall behavior. It's like capturing a symphony of cosmic notes that, when pieced together, form a harmonious picture of the event. Now let's talk about the game-changing impact of the first kilonova discovery. Picture this. On August 17, 2017, a burst of gravitational waves resembling those from a neutron star merger was detected by LIGO and Virgo. But this time, something extraordinary happened. Astronomers from around the world swiveled their telescopes to the patch of sky indicated by the detectors, and there it was. An afterglow, a kilonova, shining bright across multiple wavelengths. This was the first direct observation of a kilonova and its aftermath, combining gravitational wave detection with electromagnetic observations. This discovery was akin to opening a new cosmic chapter. It validated theories about the origin of heavy elements, provided insights into the behavior of matter under extreme conditions, and showcased the potential of multi-messenger astronomy, using different types of signals to understand the same event. In essence, the first kilonova discovery was an astronomical milestone. It demonstrated the transformative power of combining different observational techniques, opening up a new era of exploration in astrophysics. The union of gravitational wave detectors and electromagnetic observations was like a marriage made in the cosmos, deepening our understanding of neutron star mergers and the dazzling fireworks they produce. Within the heart of a neutron star merger, a phenomenon known as the rapid neutron capture process, or R process for short, is where the universe cooks up some of its most precious and mysterious elements. As neutron stars collide and merge, they unleash an intense maelstrom of energy and particles. Amidst this cosmic chaos, neutrons, subatomic particles without an electrical charge, get showered into atomic nuclei at an astonishing pace. It's as if nature is fast-tracking the usual slow process of building up elements on the periodic table. This rapid infusion of neutrons transforms atomic nuclei into heavier and heavier versions of themselves. Imagine turning a lightweight bicycle into a motorcycle with a few well-placed upgrades. Similarly, atomic nuclei bulk up, shedding their previous identities to become new elements. These newly formed elements are often radioactive and highly unstable, settling into more stable configurations over time. They release energy in the form of light and heat as they transition, adding to the brilliant glow of the kilonova. But here's where the R process reveals its true cosmic magic. This is the birthplace of some of the heaviest elements in the universe, elements like gold, platinum, and uranium. These elements are incredibly rare on Earth, but their creation in kilonovas offers a cosmic explanation for their existence. In essence, the rapid neutron capture process within kilonovas is like a cosmic forge, producing elements that adorn our world and enrich our understanding of the universe's creative powers. It's a breathtaking reminder that even in the most cataclysmic events, the universe finds a way to weave beauty and complexity into its fabric. Kilonovas are more than just stellar light shows, they're a portal into understanding the universe's history and evolution. By studying the elements they produce, scientists can unravel the intricate story of how these heavy elements spread throughout the cosmos. Remember, every element tells a tale. The abundance and distribution of heavy elements give us insights into the lives and deaths of stars, the events that precede kilonovas. By connecting these cosmic dots, we're piecing together the universe's chronicle from its very beginnings. Kilonovas are like cosmic laboratories, where matter undergoes the ultimate stress tests. These extraordinary events provide a front-row seat to the behavior of matter under extreme conditions, giving physicists a chance to push our understanding of the universe's fundamental rules to the limits. Let's dive into the physics of energy release in kilonovas. When neutron stars collide, they unleash an immense amount of energy in the form of gravitational waves. But that's not all. The extreme conditions within the collision zone, unimaginable pressures and temperatures, cause a wild frenzy of particle interactions. One of the key players in this particle extravaganza is nuclear fission, the splitting of atomic nuclei. As matter gets compressed and heated to the max, atomic nuclei shatter, releasing an enormous burst of energy. This energy manifests as the bright electromagnetic radiation spanning the spectrum from gamma rays to radio waves that we observe in kilonovas. The evolution and afterglow of kilonovas is like witnessing the aftermath of a cosmic explosion. As the energy from the collision disperses, it interacts with the surrounding matter and creates a glowing display of light. Initially, their emission is dominated by the radioactive decay of the newly synthesized heavy elements, which releases energy in the form of visible light. Over time, the afterglow fades, but it doesn't vanish entirely. The remnants continue to emit radiation across the electromagnetic spectrum, albeit at diminishing levels. This prolonged afterglow is invaluable for scientists. By analyzing its intensity, duration, and spectrum, researchers can glean insights into the composition of the ejected material, the conditions within the merger, and the forces shaping the aftermath. In essence, kilonovas are cosmic crucibles that push matter beyond its everyday behavior, revealing the hidden rules that govern the universe's building blocks. They're like extreme sports events for particles, where the universe challenges our understanding and reveals its deepest secrets. The evolution and afterglow of kilonova events serve as cosmic footprints, allowing us to trace the event's aftermath and decode the intricate physics that underlie these dazzling phenomena. Again, kilonovas aren't just captivating light shows. They're also celestial detectives that help us unravel some of the universe's most enigmatic mysteries, including the expansion rate of the universe and the enigmatic force known as dark energy. Imagine this. As a kilonova's afterglow fades over time, its brightness changes in a predictable way. This fading behavior, known as the light curve, is influenced by a multitude of factors, including the distance between the kilonova and Earth. This is where the cosmic sleuthing comes into play. By measuring the light curve's characteristics and comparing it to theoretical models, astrophysicists can estimate the distance to the kilonova with remarkable precision. This distance measurement is a key piece in the puzzle of cosmic expansion. Kilonovas essentially act as cosmic distance markers, similar to standard candles like Type 1a supernovae. The Hubble Space Telescope made groundbreaking measurements of Type 1a supernovae that contributed to our understanding of the universe's expansion rate and the theoretical existence of dark energy, a mysterious force driving the universe's accelerated expansion. Kilonovas step in to corroborate and enhance this understanding. By observing kilonovas at different distances and studying their light curves, we can trace the universe's expansion rate over cosmic time. This information sheds light on the dynamics of the universe, providing insights into the tug of war between gravitational attraction and dark energy's repulsive influence. In conclusion, kilonovas and the mesmerizing cosmic ballet of neutron star mergers have ushered us into a new era of discovery, enriching our understanding of the universe in ways we could scarcely have imagined. These celestial phenomena aren't just dazzling displays, they're profound revelations that have expanded the horizons of astrophysics and cosmology. At the heart of these cataclysmic collisions lies the remarkable fusion of neutron stars, those incredibly dense remnants of stellar explosions. The merging of these cosmic objects unleashes gravitational waves that reverberate across the fabric of space-time, revealing the secrets of these distant cosmic events. These gravitational waves, detected with astonishing precision by observatories like LIGO and Virgo, provide us with the means to eavesdrop on the universe's most intimate conversations. But it doesn't end there. These collisions give birth to kilonovas, luminous explosions that expand the electromagnetic spectrum. Through gamma-ray bursts, X-rays, visible light, and radio waves, kilonovas offer a symphony of cosmic notes, each wavelength carrying crucial information about the merger's ingredients, behavior, and aftermath. The significance of kilonovas goes beyond their visual splendor. They are cosmic factories producing elements heavier than iron, unraveling the universe's recipe for gold, platinum, and beyond. They serve as laboratories for extreme physics, allowing us to study the behavior of matter under unimaginable pressures and temperatures. Kilonovas are pivotal cosmic yardsticks, enabling us to measure cosmic distances, track the universe's expansion rate, and delve into the mysterious nature of dark energy. They're illuminating the very fabric of the cosmos, shaping our understanding of the universe's past, present, and future. Ongoing research in kilonova studies is a relentless quest for deeper insights. Researchers are refining models, simulating mergers, and analyzing data to better comprehend the intricate physics and astrophysics at play. The future is no less exciting. As technology advances, our ability to detect and observe kilonovas will become even more sophisticated, opening doors to untold discoveries. In the grand cosmic theater, kilonovas and neutron star mergers have assumed starring roles. They've revolutionized our comprehension of the universe, serving as windows into its most astonishing phenomena. These celestial spectacles remind us that our thirst for knowledge knows no bounds, propelling us to venture further, explore deeper, and unlock the universe's most extraordinary secrets. As always, thank you for taking the time to watch this video. If I missed anything or got anything wrong, please let me know, as I would love to learn more. If you liked what you heard, please consider subscribing. I appreciate the time you have spent watching this video. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of that with me. See you next time.